Hello again, students. This is Dr. DA, and I'm going to continue working on the calculations of our experiment called P8. It's the synthesis of a coordination compound. In the second part of the experiment, you analyze the compound for the content of copper and the percent copper in it. And this experiment, we are going to analyze it for the ratio of ammonia to copper. Okay, so give me a chance while I set up my view here. It's actually my iPhone serving as a doc cam. All right, here we go. So here is the procedures that you did. Please notice that there's several things here. We make the comment here that unfortunately the percent of copper in the coordination compound is only slightly different from the percent copper in the reactant. In other words, just because of the error that we had, which was about, I don't know, 5% or so, we are really not within our bounds to claim that the compound that we have is actually the compound that we say that we synthesize. The difference in percent copper is very small. So even if we have a perfect yield, we're still going to be asking, well, it's not close enough. So what we're going to take is we're going to take an alternative method. We're going to take advantage of the fact that our product should have 4 moles of ammonia per mole of copper. And so what we're going to do is we're going to calculate the number of moles of ammonia in a sample of our compound. So let's go here to our, I'm going to come over here to a blank sheet of paper first of all. And I am going to discuss what is our strategy. So let's review what is our strategy. So we're going to take a sample of our compound. Now remember, our compound is something that has, 4 molecules of ammonia connected to it. We're going to go ahead and add a little excess HCl. So these guys are going to react with the HCl. And remember, ammonia is a base. HCl is an acid. So what's going to happen is that you are going to essentially neutralize, or let's say you're going to have all of the ammonia react and react with a certain amount of acid. So we're going to have, let's say that all the ammonia reacts. And then you're going to have some residual acid. So we have residual acid in here. And what we're going to do now is we're going to find out, well, how much is that residue? So we're going to now titrate that excess with sodium hydroxide so that we can find what was the amount of residual acid in here. Since we started with an excess and we have some residual here, we can simply subtract what was our starting amount of acid minus the residual, in other words, what we titrated here at the end. And that's going to give us the amount of acid that was neutralized by the ammonia in our compound. And now that we know how much ammonia was in there, right, this is going to tell us how much ammonia is in our sample. Okay, so that is going to be our process here. So let's go ahead and do our calculations. So let me show you again a sample set of data that I have in here. And once more, I apologize. I'm not sure where I got this from. So whoever the student was that got this data, thank them, but I forget who it was, so I'm sorry. Again, remember that we did not do this part of the lab. We decided just bypass this because we didn't have enough time. So we have here, I'm going to go ahead and put numbers here. So this will be 1. This will be 2. Sorry, my printer was kind of like a little messed up. So this is the molarity of the HCl. This is the molarity of the NaOH. And these are the initial and final volumes. And again, I'm just going to skip that over here and just call this number 4. Normally it would be final minus initial, but I started at 0.00, so it's kind of like a trivial calculation. So we're going to have to find out what were the initial moles of HCl. We're going to call that number 5. We're going to go here numbering all these different rows here. 8, 9, 10, 11, 12, and a lucky 13. So here we go. Okay, let's get started. The first thing we want to find out is what were the initial moles of HCl? Now, for that, we have to go back and remember our procedures. Remember how much HCl you added? Let's go ahead and look that up. We had added 7.50 milliliters of our standardized HCl. Okay, so we're going to find out first, well, how many, where's my data sheet? I'm sorry, I have it over here. How many moles of HCl was that? Well, we said the HCl molarity was 0.4619. So again, we're going to do now item number 5 here. So we have 7.50 milliliters of HCl at a concentration, again, 0.4619. That was item number 2. 0.4619 moles of HCl per liter, but we're going to go ahead and convert that into milliliters. And let's see what that value is. Okay, we're going to put in here 7.50 times 0.4619 divided by 1,000. And that's going to give us 3.46425 times 10 to the minus 3 moles. But again, we only have 3 sig figs available here, so it's going to be really 3.46 times 10 to the minus 3 moles of HCl. Okay, so let's go ahead and copy that over here. 3.46 times 10 to the minus 3 moles of HCl. Okay, now let's see how many moles of NaOH were used. Oops, sorry, I'm going to roll this over here. This is going to be item number 6. You know what? Let me shrink this just a tad. There we go, so you can see the whole thing. So this is the number of moles of NaOH used. So this is number 6. Again, we used item number 4 times the molarity of the NaOH, which is item number 3, divided by 1,000. In other words, we used, according to our chart, 18.75 milliliters. 18.75 milliliters of NaOH. The concentration of this was 0.1032 moles of NaOH. And we're going to take 1,000 milliliters here. Again, this is item number 4. This is item number 3. And this is going to give us, let's see, 18.75 times 0.1032 divided by 1,000 equals 1.935 times 10 to the minus 3. 1.935. Now this one allows us to do the whole set of sig figs here. Times 10 to the minus 3. And this is moles of NaOH that were used. Now remember, in our strategy, that is the amount required to neutralize the residue of acid that was left after some of the initial acid had reacted with the ammonia in our compound. Let's write this over here. So this is going to be 1.935 times 10 to the minus 3. Now, since the reaction between, excuse me, between acid and base, HCl and NaOH is 1:1. Item number 7. Let's switch this over back here. Item number 7, the number of moles of HCl titrated equals the number of moles of NaOH, which is item number 6. And so this value here should be the same, 1.935 times 10 to the minus 3. Now here comes the fun part. Remember that in our strategy, however much was left over, the residue, after the reaction of acid with our compound, that is what we titrated with the NaOH. So we started with a certain amount. There was this amount left over. So whatever the difference is, that is the amount of acid that was consumed by our compound, by the ammonia in our compound. So let's go ahead and calculate that. This will be item number 8. Put it here, number 8. So this is the moles of HCl consumed by our compound. Sorry that the printing came out a little sketchy there. Moles of HCl consumed. So this will be what we started with, item number 5, minus the number of moles titrated here, item number 7. So that will be 3.46 times 10 to the minus 3 minus 1.935 times 10 to the minus 3. And I mean, I don't know if you're comfortable. If you want to switch it over to decimals, that's fine. I'm just going to go ahead here, and I had this number in my memory. I'll just rewrite it again, just to do it the same way you would do it. So 3.46 to the minus 3 minus 1.935 times 10 to the minus 3. So that's 1.525. 1.525 times 10 to the minus 3. Now, technically, we only went as far as 2 decimal spaces, 2 digits beyond the 3. So technically, we should keep that in there. So technically, this should only have 3 sig figs in the end there. But you know what I'm going to do? I'm going to cheat a little bit. I'm going to leave it at that because it's simpler to do it that way. So I'm going to put in here 1.525 times 10 to the minus 3. Okay, everybody with me? So our next step now is to find out, well, how many moles of NH3 were in the sample? Well, remember, the reaction between ammonia and HCl is also 1:1. So this is how much the ammonia in our compound titrated. So therefore, that means item number 9, the moles of ammonia in our sample should be the same as the numbers of moles of HCl consumed should be the same as 8. So we're going to say it's 1.525 times 10 to the minus 3 moles. Please feel free to pause here and there. I'm sorry, this is a little sketch. I'm having a hard time keeping the paper straight because of the way I had to set up my camera. So I keep kind of like tilting it and stuff like that. So feel free to pause whenever you need to and go over calculations. Also remember that these are calculations done with my numbers. I mean, your grams per compound are different. The molarity of your HCl was probably different. The molarity of your NaOH was probably different. So your actual values should be different, but the steps should be the same. Now, in the next step, we're going to switch a little bit here. We're going to ask, well, how many grams of copper did we have in our sample? So this will be item number 10, grams of copper. Now, you have two choices here. You can use the percent copper that you calculated in part 2 of the lab, or we can use the expected value. So for this example, I'm going to use the expected value. So this is going to be, we said, at 25.85% copper in compound. Okay, so our sample here was 0.1002 grams. So we had 0.1002 grams of compound. And we're saying, this was item number 1, and we're saying that we have 25.85 grams of copper per 100 grams of compound. So that is going to tell us how many grams of copper were in this sample. So let's go ahead and do that. We have 0.1002 grams times 25.85 divided by 100. And that gives me 0.02590 grams of copper. Again, let me repeat that. We're trying to find out in this sample how much of that mass is copper. We said that we're going to use the value 25.85% of copper in the compound, but whatever you found in part 2, you may want to use that one instead, kind of like keep it all in the house. But I'm going to use this one just for the sake of this example. So this is how many grams of compound I have based on item number 1. And this is 25.85 for every 100 grams. That is how many grams of copper we have in here. So let me go ahead and copy that over, 0.02590. And now we're going to find out how many moles of copper we had in the sample. Actually, I could have done some of these steps kind of bundled in, but I wanted to split them to keep us kind of like a little, make it easier for us to follow along. So we're going to do now item number, let's see, that was item number 10. We're going to do item number 11, which it says here is the moles of copper. So we're going to do item number 10, which is 0.02590 grams times the molar mass, right? Right? Well, not times the molar mass, but actually we're going to divide it, right? Okay, just want to keep you honest there. So 1 mole of copper is 63.55 grams of copper. And oops, sorry, I don't want to cancel out the number. I just want to cancel out the units. So let's see what that is. So we have 0.02590 whatever divided by 63.55. And that's going to give me 4.075. I'm going to keep it in there. 7. So we're going to round that up times 10 to the minus 4. moles of copper. Okay, just pause the video if you need to. I'm going to write this number down here. 4.078 times 10 to the minus 4 moles of copper. Okay, so we now have the moles of ammonia in the sample. We have the moles of copper in the sample. So now we need to do is find out the ratio of ammonia to copper. So we're going to take the moles of ammonia in the sample, which was item number 9, divided by the number of moles of copper in the sample, which was number 11. So we had 1.525 times 10 to the minus 3 of ammonia divided by 4.078 times 10 to the minus 4 moles of copper. And let's see what that glorious number gives us. 1.525 to the minus 3 divided by 4.078 to the minus 4. And that gives us 3.739. So let's 3.940. And that's the ratio we get. Now, don't forget we cheated a little bit here, right? So technically, this number here that we said, we should have been only 3 sig figs. So these numbers should only be 3 sig figs here. So I'm going to go ahead and write down here the ratio as 3.74. That is, in my sample, the number of moles of ammonia for every mole of copper. Now, number 13, again, we know that the percent error, again, is going to be the experimental value we got minus the real value divided by the real value times 100%. And don't forget that the compound is supposed to have 4 moles of ammonia per mole of copper. We got 3.73. And that 4 really should be exact, so we don't have to worry about sig figs there. Okay, times 100%. So let's see what that gives us. 3.73 minus 4.00. That's going to be negative 0.27, which means we have only 2 sig figs available. We want the absolute value of that. So we're going to divide that by 4.00 times 100%. And we get an error of 6.8%. This is going to be here 2 sig figs. When you did the numbers, you could realize that. And again, like I said, with your values, you can work whatever you decide. Remember that you may have used a different calculation of the percent copper. So this is going to be an error of 6.8% here for our results. Cool. Okay, again, I went at a fairly brisk pace here, but I'm hoping that you guys don't mind. We're going to let you now work with your numbers, please. You are on your own, and hopefully what I just explained here made sense. Hopefully you took notes. Again, don't forget, you are working with your numbers, not mine. So you may or may not get similar values to what I got with this data set that I put out here. Again, if you have any questions, send me a message or bring them to our session this week. Thank you very much.